Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 7, Analysis of Covariance, Comparing Regression Lines. So, analysis of covariance is multiple regression, where you have a numeric response variable, and as predictor variables, you have at least one continuous variable and one categorical variable. And what that will create is a regression line, potentially, for each category of that categorical response variable. And so this chapter is about fitting those sorts of models as well as asking what sort of model is the best, so model selection, and doing the multiple parameter hypothesis tests required to compare regression lines. So, as a trivial example, let's look at, and also this is a made-up example. Let's imagine we have some tool data where we're looking at the lifetime of the tool with respect to how fast that tool is spinning, RPM, revolutions per minute, as well as the type of tool. And if we were to do a simple one-way ANOVA of that tool, and so there's the data, but if we plot it just as we've got the lifetime of the tool, and we've got tool A, which seems to have a short lifetime, and tool B, which has a much longer lifetime, about twice as long, and we do a t-test of that, we find that there's a big difference, obviously. Okay, significant p-value. The observed difference is about 15 or 16 or so. But the problem is that, in fact, these two tools were operated at different speeds. So that's what this paragraph says. So if we plot the data, I'll zoom out just a little bit. So we have type A, which is red in letter A, and the blue color B's are up here. And we've got speed, so the RPM on the horizontal axis, and the lifetime hours on the vertical axis. And so we see actually that A and B follow the same pattern, that the faster you operate the tool, the less the lifetime is in hours. It sort of makes sense, actually, if in fact, one rotation wears the tool by a certain fixed amount regardless of the speed. This might be what you would expect, that as you increase the speed, the number of hours would decrease. In fact, you might actually expect something to be a little more severe than this. That faster and faster speeds because of heat and so on, blah, blah, blah. Okay, but the point is that it's plausible that if you were to operate tool A at these slower speeds and tool B at these faster speeds, that you get the same pattern. So there may actually be no difference between these tools types A and B. It might, in fact, just be a function of the speed that they're operated on. Okay, so it's important, as we saw in Chapter 6, to adjust for the things that you can't control. So speed is another variable in addition to tool type that affects the hours, the operation hours. Okay, that's what that paragraph says. Great. So that brings us to analysis of covariance. How do we include variables, both continuous and categorical, into a model to predict a continuous response variable? So the first thing for us to think about is how to write a model with a categorical variable. And we'll be looking at indicator variables. In fact, I'm even surprised I put the word dummy variable in there, though that is what other people tend to call these things, but I call these indicator variables. This is, an indicator variable is a variable that takes a value 0 or 1 depending on whether a certain condition is met or not. So you assess a Boolean statement, true, false. If it's true, the indicator variable becomes a 1. If it's false, the indicator variable becomes a 0. So one way we can model the tool lifetime data is by an intercept. So that is, so we have some baseline category, which will be the intercept. We have RPM, so that's the continuous variable that takes any number, looks like from the data from somewhere around 500 to 1,000 RPM. And then we have type. And the type, we had tool type A and tool type B. In this notation that I've used here, type B indicates that when the type is B, then this variable, the indicator variable, will be a 1. When it's type A, this indicator variable will be a 0. So that leads us to two different models depending on the type of tool. So just to explicitly write that out, if type was A and this equals a 0, we'll rewrite down here, so for type A tools, that type B is a 0, and so the model simplifies to just beta naught plus beta 2 RPM. And for type B tools, that indicator is a 1, and notice what happens here. That 1 gives you beta 1 and beta 0. Those are both scalars all by themselves, and so those add together. That represents a difference in the intercept. Notice that beta 2 is the slope regardless of whether it's tool A or tool B. So this model gives us two regression lines, one at intercept beta naught, the other at intercept beta naught plus 1, but they both have the same slope. All right, so we're talking about parallel regression lines. And that's what all that stuff says. Oh, maybe to be specific here, beta 1 is the difference in intercepts between the two models, between the two tool types. So that's what this line down here says. So that would be an example of a result that could come from this model. This doesn't represent the data that we saw before. It's just an example of what that model could look like. Okay. So in this case, beta 1, whether that equals 0 or not, beta 1 is the difference in intercept. So that ends up being the parameter of primary interest, that this tells us whether tools are different after adjusting for the speeds that the tools are operated at, assuming that in fact a model that has parallel slopes, that has the same slope for each regression line, that's the appropriate model. All right. So here is, I think this is a, let me page up for a second. So there's this fake data set, and then tools, page up again, tools fake. Okay, so there's another, so this is the tools fake data set. There's a second data set, paging down, called tools, which I don't have the code here to read that in, but it is in the R code for this chapter. And here's the data for these two tool types. Okay, so this is the real tools data. We've got RPM on the horizontal axis, we have lifetime on the vertical axis, we have tool types A and B as red and green. And notice one detail here, as someone creating a plot, it might be nice to actually change the order of these two plot types in the legend so that they correspond with the order that you observe them in the plot area. Okay, and so you could do that by simply changing the baseline group to B, and that would end up being the first variable again. Okay, so that's a small aside, but those small differences can make a real big difference in terms of how quickly someone can interpret a plot. Okay, but what do we see? We see plot tool type B seems to have a much higher lifetime than tool type A. They have similar slopes, but not quite the same. In fact, you sort of expect that because A is closer to 0 vertically on the lifetime axis, and at some point you can't hit 0, so this probably will flatten out. But so we can fit this model. Let's see, so we're fitting a model here that's RPM plus type. And that's the model that we just specified above. We had main effects for RPM and type. I'll zoom in again. And when we evaluate that model in terms of the terms that are significant, okay, we're not assessing model fit at this point, we find that the main effect for RPM is significant, and the intercept for type B looks like it's about 15 units larger than type A, and that is a significant difference. When we assess model assumptions, looks like we may have one influential observation for tool type B, largely because it has a large leverage. But otherwise the assumptions seem quite reasonable. A tends to have a little bit less variance than B. This is suggesting that the mean or the lifetime scales, that is, the variance scales with the mean. So we might consider looking at a transformation at this point. If I page up for a moment, the variance of B around its regression line is larger than the variance of A around its regression line. And that's because this lifetime, right, tool type A is down near 20, tool type B is up around 35 or something, and because tool type A is closer to 0 and you can't go negative, the variance must end up being less at those lower values. That's simply basically a constraint of having positive only values for lifetime. So maybe a transformation would be interesting here. Page back down. Okay, but just continuing. So the fitted relationship, this is the fitted model, and I'm just pulling that directly from, can't quite get everything on the same page. Here's the intercept, 36.98. Here's the RPM, negative 0.02, and type 15. Okay, so those are the coefficients. If I page back down to that model, I've just plugged those numbers in as the coefficients here. And then for the different tool types, tool type B and tool type A, I'm going to solve for this indicator variable. And when it's tool type B, this indicator variable is a 1, so we end up adding these two intercept terms together, minus that slope. Whereas tool type A, this indicator is 0, so this 15 never enters into the intercept. So those are the two fitted regression models. And we've tested whether beta 1 equals 0. We rejected that null hypothesis and concluded that the intercepts were indeed different. All right. So I'll come back in another video to discuss how we generalized the ANCOVA model, the analysis of covariance model, to allow unequal slopes in all the variety of models that can be fit when you consider having main effects for slope, intercept, and their interaction.